Hello, my name is John Scotto, and today we'll be going over the XL-18 flamethrower phase 2 part of the project. My group members are Taylor B. and Ethan Myers. For the contents, we're going to be going over the heat transfer mechanisms, the overview, mathematical modeling of system, numerical analysis of system, suggestions for improvement, and the concluding statements.
For the mechanisms of heat transfer, as Kato said earlier, this system contains all three main primary modes of heat transfer: conduction, convection, and radiation. Conduction is apparent in two different parts of the system, first being the fuel tank and fuel interface, and the second being the atomized fuel and ignition flame interface. As we can see in the diagrams I have below, the first one being on the left-hand side, the actual fuel tank and the fuel interface, where we can see the heat being transferred between the fuel tank. And then the second one, as we see the fuel moving past the ignition flame, and it brings with it the warmer air. On the math side of things, and this math gets modeled through Fourier's law. Fourier's law states that the heat flux in one dimension is equal to K, which is the thermal conductivity, is an intrinsic property multiplied by the temperature gradient. The temperature gradient will be expressed as T2 minus T1 over L, since this is in one dimension. As also, because we are choosing to say that we are going from a hotter temperature to a cooler temperature, the cooler temperature is in the surroundings, we have to use a negative. But all in this can be expressed as the thermal conductivity multiplied the difference in temperature over L. In regards to convection, convection occurs in the third stage of the system. Convection is the transfer of heat through the movement of fluids. So as the fuel meets the ignition flame, the flame then surrounds the air because of the forced convection. Whereas here now we have hot gases being dispersed. It's increasing the flame's reach and intensity, and this is typically what we see as the flame. So here we can see I have two different diagrams. First one just showing general forced convection, and the second one is of our actual system, where we have the cooler temperature T1 in the forced air supply moving through the flame, coming out, we have T2, and then we can see that T1 is cooler than T2. In regards to the math of this, we use Newton's law of cooling to model it. So Newton's law of cooling states that the heat flux of convection is equal to H, which is a property called the convection heat coefficient, multiplied by the difference in the surrounding and the surface temperature. So the sign convention is presumed that we have a positive heat flux energy, which states that heat is moving away from the surface. So essentially that way of a warmer surface. However, this could be changed pretty easily. You just have to swap the two terms in the parentheses. Moving on to our last mode of heat transfer. Radiation is present in the last stage of the system. Radiation transfers heat from the flame to a distant target, which impacts area beyond the direct contact through radiative heating. Radiative heating moves according to wave-like behavior. Essentially, we can think of it as you drop a drop in a bucket and you can see a wave propagate out. That's essentially what's happening here. So in our first diagram, we have the heat, and you can think of it as a cloud, and it's radiating out towards the cooler surface in the blue. However, we also need to note that because of this, we are also having a component of convection also occurring simultaneously as a component of the radiation. For the math theory of the radiation heat transfer, we use the Stefan-Boltzmann law. So the Stefan-Boltzmann law states that our radiation heat flux is equal to Q over A, which can then be expanded into our bottom form, which is emissivity times the Stephan-Boltzmann constant times the difference of the surrounding and the surface temperature, but they're both raised to the fourth power. So this might be a little bit easier though to express in terms similar to that of the convection, where we can have it then combine the two terms, because as I mentioned earlier that we have in this case we have both a component of convection and a component of radiation together, so it's easier to express them both in similar fashion.
Okay, to model our flamethrower, we went with the three basic heat transfer equations, those being the ones for conduction, convection, and radiation. So we went to the manufacturer's website and they had some basic information for us to use. The flamethrower is difficult to model the same because it varies from, what's the oxygen pressure in the atmosphere at that altitude? Is it windy? Has the flamethrower been sitting outside and it's gotten super warm? That'll affect the CO2 pressure in the canister and the pressure of the fuel sitting there waiting to be burned. And then also the mixture will vary too. So like napalm will burn very slowly, but once it gets on something, it's going to keep burning. Diesel will burn very consistently, and gas will burn very fast. So we kind of just combed through the website and what their measurements were, and we came to these basic equations we're going to use. So for the fuel, we just assumed it was going to be just a little bit warmer than its surroundings. That'll be 300 Kelvin. The environment's like 298 Kelvin, so just ambient air temperature, room temperature. And then we assumed the flame being the most common one, the diesel that they offer, without, if they preload a tank and send it to you, it's going to be diesel. We just assumed, based off of their estimates, that it'd be about 2,000 degrees Kelvin on average, on an average day. Okay, so we got our three basic heat transfer equations, and we got our four stages to represent this heat transfer of the flamethrower. So the first stage is conduction between the environment and to the fuel tank. So if you can imagine, if you have a flamethrower and you put it in a giant freezer overnight, it's going to burn with a little less passion than if it had been sitting out in the sun. Now, that might not be a huge noticeable difference because it's still a flamethrower, but it might make a difference in it, say, starting or burning as it's intended. So we included it. So we did the conduction heat transfer equation between the fuel and the environment, and that came out to be negative 120 watts per meter squared. And then for our second one, we did conduction as well, and that being between the flame holder, or at the beginning of the flamethrower going off, and then the fuel, which is passing through it. So once the flame holder is constant, and some flamethrowers it'll just be like a little spark, and then once it gets going, it's just the flame on the other side of the holder that gets it going. But in this case, it's the flame holder, and that's consistent. So that came out to be the amount of energy released by that came out to be negative 1,000,000 and change watts per meter squared. And now for our third one, we did convection between the flame and the environment, that same environment being the one that had the tank heated up for stage one. And that came out to be 170,000 watts per meter squared. Now, for our first stage, which was radiation, by the way, we just used, if you ever do these calculations yourselves, there is a heat transfer coefficient, that being K for conduction, H for convection, and sigma for radiation. But in radiation's case, there's also epsilon, which represents the Stephan-Boltzmann constant, which you just look up, and just matches the rad units. And that came out to be something that is hiding behind my little head thingy. But the total, when you add them all up, Q1, Q2, Q3, and Q4, comes out to be around negative 34,000 watts per meter squared. So quite a lot of energy is being released by this flamethrower.
In regards to suggestions for improvement, we have 6 different suggestions that we can offer. And then the 7th one is a combination of all of them. So first one is optimizing the ignition temperature. Second, enhancing the fuel atomization. Third, would be optimizing the fuel nozzle. Fourth would be applying thermal coatings. Fifth would be radiative reflectors. And sixth would be fuel preheat. For the optimization of the fuel, the ignition temperature, doing so, we would be able to change the temperature that the torch burns at, which we can then change and kind of optimize and see, what's the best for that. For fuel optimization, we're able to look at nozzle designs and ensure that we can get a more complete combustion, which kind of ties into the fuel nozzle. The fuel nozzle can also apply towards to the actual fuel itself being dispersed outside of the flamethrower. So in that one, you can have one that's more of like a fanning one, or maybe more of like a long shooting style one if you need to get further reaching. Fourthly, for the thermal coatings could be used to apply to the actual system itself to help improve the thermal efficiency and then improve performance. Fifth, the radiative reflectors would help dissipate and I guess prevent radiative heat going to areas that we don't want it, because heat travels radially, so it happens in all directions. So you're able to kind of reflect it and change it and kind of fine tune it to the correct direction. And then lastly, we could preheat the fuel so we can ensure more complete combustion.
Concluding statements. The XL-18 flamethrower uses all 3 primary mechanisms of heat transfer: convection, conduction, and radiation. Using Python, we numerically calculated and evaluated the different stages of the following system. For Q1, we got negative 120 watts a meter squared. For Q2, we got negative 1.02 megawatts a meter squared. For Q3, we got 170.2 kilowatts a meter squared. And Q4, we got 816.1 kilowatts a meter squared. Some suggestions. Some suggested improvements include fuel optimization, optimizing the nozzle design, and radiative reflectors. We appreciate the time that you guys take out of your day in order to watch our presentation. Just wanted to say thank you. Take care and have a great day.